All right, my friends, welcome back. Sorry for that interruption. My 5-year-old needed some attention. So let's keep talking about graphing those rose curves. And in the previous video, in example 5, we graphed this using a t-table approach. And so now what I'd like to do is in example 6, give you an illustration as to how we could get closer to doing something like this without doing the t-table approach. Because with rose curves, I love t-tables for most polar graphs, but I don't love it for rose curves. So for example 6, I'd like to do an exercise here with you, and this should help review something that you were good at one time. So for part A, I'd like to have you graph y equals 2 sine 3x. And I'd like for you to graph it strictly for all x from 0 to 2 pi. So, and I guess, I don't know, soft bracket, I guess. Okay, so, and I'll include this graph paper. It's just kind of nice for getting this done. So let's recall, how do you do this? So what does a sine wave look like, first of all? So sine wave, just one full period, looks like this. And typically it takes a full rotation, so from 0 to 2 pi to get through one full cycle. But when you graph sine of 3x, the 3 multiplies your angle measure by triples your angle measure before you take the sine. So it causes this curve to go through its cycle in 1/3 of the amount of time. So the period ends up being 2 pi over 3. And then remember, since sine is easily broken into 1, 2, 3, 4 pieces, a handy tick mark value would equal your period divided by 4, and your period here is 2 pi over 3, and dividing by 4 is like multiplying by 1/4. So if you cancel this down a little bit, you end up with a handy tick mark value being pi over 6. So So 1 pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6 reduces 5 pi over 6, 6 pi over 6, 7 pi over 6, 8 pi over 6, 9 pi over 6, 10 pi over 6 would be 5 pi over 3, 11 pi over 6, etc. Okay. Now for graphing the function, we decided it would go through one full cycle in 2 pi over 3. Also, after you take the sine, which normally would max out at 1 and -1, we're supposed to double it. So this should reach, let's see, so here's your vertical center. So this should reach a maximum height of 2, and then this should reach, an amplitude essentially of 2. So when you graph it, we'll just kind of do starting at 0, stopping at 2 pi over 3, and then showing an amplitude of 2. So it's just a sine wave that got sped up, essentially amplified and sped up. And then we'll just copy 1, 2, 3, 4, just kind of copy off of ourselves. Okay, there we go. Okay, so that would be on a rectangular plane, just the graph of y equals 2 times sine of 3x. Now what I'd like to talk with you about is, and yes, this is very much related to example 5, but let's talk about getting closer to not needing a t-table for rose curves. So let's talk about if I was to ask you for part B to graph, now watch what I'm going to do. I'm going to take y out, put r in. I'm going to take x out, put theta in. So otherwise it's the same. R equals 2 sine 3 theta. And then we're going to talk about for all x from 0 to 2 pi, okay? Now, that is exactly what you graphed in example 5. So you definitely know a beat it to death version of how to do it. But let's talk about the relationship between this graph and take a minute and think about that for yourself, please. And now let's talk about what does this on a rectangular plane, how does that translate over into a polar plane? So notice that here your y, which here would be your r value, was 0 when your angle was 0, or when your x is 0, which would turn into the point 0, 0 over here as well, which would just be the pole. And then your output value, here y, but here it would be r, increased until it reached a maximum r value of 2, and it reached that at pi over 6. And then it started decreasing as your input x increased to pi over 3. So it went from 0, 0 to pi over 6, 2, back down to pi over 3, 0. So what would that look like over here? It would go from 0, 0 to pi over 6, 2, and then back down to 0, 0 at pi over 3. And I'll put little dashed marks to kind of show the places where your graph got sucked into 0. But so the story is as your angle increases from 0 to pi over 3, first your output value, it grows, and then it decreases back down to 0. And so that would turn into essentially this first petal right here that we had, okay? And so I'm going to number this petal 1, and I'm also going to number this petal 1. And there's a reason that we're doing that, okay? Now let's talk about this graph right here. So the graph here went from pi over 3, 0 to pi over 2, negative 2, to 2 pi over 3. And what would that turn into? So we're plugging in values from pi over 3 to 2 pi. So that would be from pi over 3 to 2 pi. But you're getting negative outputs. And so you go from 0 to negative 2, back to 0. And so this part of the graph, I'll call this petal 2, this part of the graph created petal 2. And then from 2 pi over 3 to pi, that would be from here to here. You go from 2 pi over 3, 0. Your output increases gradually till you max out at 2. That happens at 5 pi over 6. And then it decreases back down to 0. So it goes from 0, 0. At 5 pi over 6, you'd have an r value of 2, and then it gets sucked back into 0. Like so. And so that would be petal 3. So notice we got those 3 petals nice and evenly spaced, all with a petal length of 2, all when we were only halfway around the unit circle. So the question is like, what's all this stuff for? So let's think about that. So here you go from pi to, what on earth does that say? Pi to, I probably labeled that wrong, 7 pi over, did I start putting 8s? That's weird, okay. Should say 7 pi over 6. Sorry, guys. And then, there we go, 4 pi over 3 because, okay, so an 8, okay. There we go, okay. Sorry, guys. Okay, so from pi to 4 pi over 3, that makes a little more sense now. I'm going to use a second color here, maybe purple. So from pi to 4 pi over 3, notice we go from 0 to increasingly negative r values and then back to 0. And so from pi to 4 pi over 3, because you would get these negative r values, you would have redrawn petal 1. And then what would happen between 4 pi over 3 and 5 pi over 3? So from here to here. Here, for this part of the graph, you go from 0 at 4 pi over 3 to increasing gradually until you get to 2 at 3 pi over 2, and then back to 0. So that would mean you'd go toward 5 pi over 3, or sorry, toward 3 pi over 2, and then back. So that means that this part of the graph resulted in petal 2 again. And then this last part from 5 pi over 3 to 2 pi, getting negative R values means that you would have been going away from those angle measures, and so you would have gotten petal 3 again, like so. Okay, so just a minute, honey, I'm making a video. Okay, thank you. Okay, sorry guys. Okay, so what I wanted to show you here is that you halfway through for an equation like this one, halfway through you'd already created petals 1, 2, and 3, and then the second half of the unit circle you just created petals 1, 2, and 3 again. So it basically draws itself twice when you go around the unit circle. And then also I wanted, if you look at the numbering at the top, it's going to lead to the shortcut that I'd really like for you to know. So to get these graphs, really what I like to do is just find where the tip of each petal is, which I hope you can see from this picture. You could seriously just look for petal 1, 2, and 3. You could just set your R value equal to either +1 or -1, not both. You just want one or the other. And it would help you find where the petals are, okay? So we'll make that part C, okay? And it's gonna be, I know we're gonna like beat this problem to death here, but the whole point is to get to this full expression of how to do this for part C, okay? So we are going to show how to find the tip of each petal of R equals 2 sine of 2 theta algebraically. And then this would lead to a very quick way to graph Rose curves. Oh, that's not a 2. Sorry guys, that's a 3. Okay, so if you're finding the tip of each petal, then really what you could do is just set your R value to what you think the maximum value over here would be, and I hope it makes sense. The coefficient will be the biggest value you can get over here, since sine only goes between -1 and 1. So really what you could do is you could just set R equal to 2. And to make sure we're clear, we're really just looking for these peaks on a rectangular plane that would turn into the tips here. So if you set R equal to 1, so I'll recopy. Actually, I'll put it right underneath here. So you're just going to set R equal to 1. Sorry, R equal to 2, that is. And then we're going to solve for theta. So divide the 2 over. And then don't let the 3 theta freak you out. It's just the name of an angle. So we're looking for when the sine of your angle would be 1. So think about that. Here's your unit circle. When would your sine be 1? So basically 3 theta, which is the name of your angle, could equal pi over 2. It could also equal, I mean, honestly, it could be pi over 2 plus, what could you add to pi over 2 to get back there? Infinitely many times. So you could add 2 pi n, any multiple of 2 pi. And then you could divide both sides by 3. And then what would you have? You'd have pi over 6 plus 2 pi over 3n, and then that would be true for all n from the set of the integers. Now really quick, let's just think about what this is saying. If you had done this work in the first place, instead of t-tabling it out like we did in example 5, or instead of drawing it on an xy plane and then having that translate into a polar plane, if you had just done this fairly quick work that you've done in the past anyway, how would that translate to your graph? Well, it would tell you, like, you could just start using your own rule here and start plugging in integer values for n, like 0, for example. If n was 0, it would say theta is pi over 6. And so you'd know at pi over 6, you get an r value of 2. And then what is this really saying? It's saying basically every third of the circle, you'll end up with another tip of the petal, which I hope makes sense with what we've been doing anyway, since from the get-go, these guys have been evenly spaced, you know, and there's only 3 petals. So let's look at that. So if you were to let n be 1, for example, you'd have pi over 6 plus 2 pi over 3. 2 pi over 3 is like 4 pi over 6, so added in, you get 5 pi over 6. And so if you go to 5 pi over 6, you would have an r value of 2. And then let's let n be 2. 2 times 2 pi over 3 is 4 pi over 3. Put it over 6, you got 8 pi over 6. Add it to pi over 6, you got 9 pi over 6, which reduces to be 3 pi over 3. And there you go. You've got another place where your r value would be 2, because that is what you were solving for, is when your r value would be 2. And then when would your r value be 0? It would be 0. You could solve, I guess, if you want for when r is 0, but really it kind of doesn't matter, because you're just looking for, you'd go out until you get to the tip of a petal, and then you go out till you get to the tip of a petal, and then you go out till you get to the tip of a petal. And so this would be a decent sketch for a test question, just having, in a way, 1 point of accuracy per petal, and then you'd have it. So a quick summary for what we're doing here. So these don't look much like roses to me, but whoever was in charge way back in the day decided that these would be called rose curves. I would have called them daisy curves personally, but rose curves have equations of the form r equals some arbitrary constant times sine of n times theta, or r equals some arbitrary constant times cosine of n theta. And then let's think about what would the a value cause. So if you look at the example that we've done here, you had a 2 out front, and then that ended up being your maximum r value, which ends up being the length of each petal. So I'm going to say absolute value of a, though, because you could have a negative r value there. So absolute value of a is the length of each petal. And then we have a little more talking about what n means, but you're going to see as we move to example 7 that if n is an odd number, like it was in the example that we just did, so where you had, what was it, a 3 there. If n is odd, then the rose curve, then rose curve will have exactly n petals. And what we're about to demonstrate in the next example is that if n is an even number, then your rose curve will have double that number of petals, and we'll demonstrate that in the next example. Oops, sorry guys, I was off the screen there. Okay, and we'll talk about how that would affect your algebraic work for graphing something that has an even multiplier on your angle there. Okay. Okay, so let's move on to example 7. Okay, part A, let's have you graph, and we're going to go back to an xy plane. We're going to have you graph y equals 3 times the sine of 2x for all x from 0 to 2 pi. And then, so that's on a rectangular plane. So that would be on one of these guys. And I'll include this as an attachment to make sure that you'd have access to that. So go ahead, and this would be a good time to pause the video and see if you remember how to do that. But I'll go ahead and show my solution here. So, you know, again, we have a sine wave. You know, it would normally take from 1 full rotation, you know, the unit circle, to get through the cycle. But you're doubling your angle measure, so it's going to go through this process twice as fast. So that means that it would do it in half the amount of time. So the period here, the amount of time it takes to go through one complete cycle would be pi. And then again, because sine and cosine, actually all the trig functions, are easily broken up into 4 easy pieces, that would mean a handy tick mark value would be 1/4 of the period, so pi over 4. Okay, so if you look at the graph paper that I have here, here's 0 to pi over 2, so halfway would be pi over 4. So 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4, 7 pi over 4, and then 8 pi over 4 lands you at 2 pi. Okay, so graphing this guy, keep the 3 would triple your heights, so that means it would create an amplitude of 3 there. Okay, so 0, and then we said the period was pi, and then the amplitude is 3. And then hopefully this seems familiar, or it's maybe some much needed review, one of the two. Okay, so this is the graph and on a rectangular plane of y equals 3 times sine of 2x. Now, if you paid attention to the summary that I just wrote, for part B, if I was to say graph, which I am going to say, r equals 3 times sine of 2 theta, so all of a sudden it's on a polar plane, for all x from 0 to 2 pi, we're going to go back to the relationship between this and its polar graph, okay? So if you went back to the summary though, how many petals would this have since this is an even number? So the summary said that if you have an even number here, if n is 2, then you'll have 2 times that number of petals. So according to the summary, we should have 4 petals. Let's talk about how come. So if you look at the picture up here, from 0, you'd have 1 petal that starts at 0, 0, stops at pi over 2, 0, and then halfway in between at pi over 4, it has its maximum r value of 3. So what would that look like? So you'd have, I'll just do this little dash line here to show places where the graph got kind of sucked in to 0. At pi over 4, 1, 2, 3. And then you'd have a graph that gradually grows to a value as your angle grows. Your r value grows to a maximum value of 3, and then it shrinks back down to 0 as your angle increases. So this looks like your angle increasing, r, as angle increases, r increases, hits a maximum value of pi over 4, 3, and then as your angle increases, you get sucked back into 0. So if you label it, then this would be, this part of the graph right here would be how we got petal 1, right there. All right, now let's look at this graph right here, from pi over 2 to pi. So pi over 2 to pi, you go from pi over 2, 0 to pi 0, but you get all negative output values until you get to a greatest magnitude of 3 here, but it's -3. So what would that mean? That would mean that when your angle rotates from pi over 2 to pi, you're getting points that are coming away from these angle measures. So you would go from, so when you graph 3 pi over 4, -3, and then this would be the petal. So I'm going to label this as petal 2, and this is the petal that results from this part of the graph right here. So I'll just label that as a 2. Okay. From pi to 3 pi over 2, here's pi, here's 3 pi over 2. You're back to positive R values, so your petal would go toward these angles right here with a maximum R value at 5 pi over 6, 3. So, wait, 5 pi over, sorry guys, my goodness. 5 pi over 4, 3. Good night. Okay. Okay, so here's petal 3. Okay, and then 3 pi over 2 to 2 pi, so that would be quadrant 4. You're going from R value of 0 to negative R values that have a greatest magnitude of 3 and then back to 0. And so for quadrant 4, your graph actually shows up in quadrant 2 with the tip of the petal being at 3 pi over 4. So this would be petal number 4. Okay, and so here you have it, an example of your n value, that is, being even, and then it was a 2 and we ended up with 4 petals. And so part of the reason that I had you do these XY planes is so that you can see that when you have an odd number, when you are halfway through the unit circle, you really have already graphed all of your petals that you're going to get. And so I hope you can imagine if you had like a 5 instead of a 3, it would be a very similar story here. And then with even numbers, when you're halfway through, you don't have all of your petals. You only have half of them. You get different petals from the rest. And so that's actually going to affect when we go to part C and we're talking about, hey, you know, how can you do this algebraically instead of having to work so hard? When you go to part C, I think I'll put part, I'll put it here. Part C, let's have you show how to find the tips of each petal of R equals, same problem, we're just going to beat this sucker to death here, of this graph. And this is really what I'm going to be hoping you'll do when you get to your test. I'll probably actually specifically call for you to demonstrate that you can do this. So this is really supposed to help here. When you have an even number being multiplied on theta like this too, you're going to get different petals from R equaling 3 than you would from R equaling -3. So your algebraic setup will be different. To find the tip of each petal, when you have an even number here on theta, you're going to set R equal to +3 and -3. How come? Because you get different petals from +3 and -3. So your algebraic setup would be substituting plus or minus 3 in for R. Like so. And then divide both sides by 3. And then I would consider this unit circle ready. So you're going to think about the unit circle. When is sine equal to plus or minus 1? it would be when your angle, which here is called 2 theta, is equal to pi over 2. And then I'm just going to go ahead and say, you know, here's pi over 2. And if you add any multiple of pi, you'd get back to that location. And then let's divide both sides by 2. So we'd have theta would be, divide that in, you'd have pi over 4 plus pi over 2n for all n from the set of the integers. Okay, so how could you turn that, and I hope that feels relatively quick, you have done that before, so how would you turn that into a graph instead of having to work so hard like we have in the past? You could just start playing around with easy integer values and plugging them in for n, like 0. So if n was 0, you'd have pi over 4. So that means that at pi over 4, you'd have a tip of a petal. And then you could plug in another value for n, like 1. So pi over 2 times 1 is pi over 2. That's the same as 2 pi over 4. Add it to pi over 4, you have 3 pi over 4. So at 3 pi over 4, you'll have another tip of the petal. Let's increase n by 1 again. So we just plugged 1 in. Let's plug 2. So 2 times pi over 2 is pi, plus pi over 4 is 5 pi over 4. So you'll have another tip of the petal at 5 pi over 4. Am I going far enough? No. Sorry, guys. We set this up to be, the tip of the petal should be at 3 this time. Sorry, not at 2. So at 5 pi over 4, 1, 2, 3. So we'll go toward a 3. And then, you know, at this point you can kind of see where the last one's going to go, but that's okay, we'll behave. So if n is 3, you'd have 3 pi over 2, which is 6 pi over 4, add it to pi over 4, you have 7 pi over 4, so 1, 2, 3, at 7 pi over 4. There you go. And then for filling it in, you could figure, you know, that you would have r values of 0 halfway through, so some people like putting these little dashed lines in where the zeros would be. It's not required at all. But you do want to make sure that when you fill it in, that you fill it in with petals that don't overlap. You know, and you can see that's definitely not going to win any beauty contests anytime soon. I'll try to fix that a little bit. The petals really ideally should be symmetric and they should be congruent, which these are not. So we're just going to pretend that this looks amazing. There you go. Whatever. Okay, but that would be a way to get that graph pretty quickly. All right, my friends. So before we close this video out, I'm just going to give you one more practice problem where you don't have to do a t-table, you don't have to do an xy plane, you can just do the algebraic finding, you know, the tips of the petals type deal. So this would be example 7, I think. And for part A, let's have you graph r equals, let's do 2.5 times sine of 4 theta. Okay, super good time to pause the video and just see if you can figure that out. And have I used all of my polar graph paper? No, I have this piece left. And okay. All right, my friends. Okay, so I'm gonna go ahead and go through this. I would algebraically find the tips of each petal, or the tip of each petal. Analyze it first. So it's a rose curve. You have an even number here. So we're expecting how many petals? 8 total. And so you're going to get some petals from r being positive 2.5 and some petals from r being negative 2.5. So we'll set that up. Divide the 2.5 over. Think about the unit circle. you're looking for sine to be plus or minus 1. So set your angle, which is 4 theta, equal to pi over 2. And then you can see you just keep adding multiples of pi to get other solutions. Divide both sides by 4. So you should have a tip of a petal at pi over 8. And then if you add any multiple of pi over 4 to that, as long as your n value is an integer, then you should have another tip of the petal. Okay. And when you're done with these, things should make sense. You know, you're expecting 8 petals. So when you get to here and you kind of obediently do what this says, then you should have 8 petals. And how long should each petal be? It should be 2.5 units long. So, so if n was 0, then you'd have pi over 8. So where on earth is pi over 8? Well, if this is pi over 4, and it took from 0, it took 1, 2, 3 spokes, then pi over 8 would be like halfway. I hope that makes sense, everybody. So you're going to go toward pi over 8, 2.5. So that would be your first one. And then it says to basically keep adding pi over 4s. So, and pi over 4 is 3 of these spokes. So I'm just going to go 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. And I get back to where I was. And then, you know, halfway, so like at pi over 4, at pi over 2, you know, etc. Wait, pi over 2? Yeah. You would have places where you would have had it like get pulled into 0. So now I'm just going to try to fill in petals. I hope it makes sense. The more petals you have, the skinnier they are. And then I just kind of pull them in. And then really you're just trying to draw something that kind of has, you know, that rose curve shape. And then you really want to make sure that your petals don't overlap when you draw them. So just do your best there. There you go. 1, 2, 3, yeah, okay. And, you know, not going to win any beauty contest, but it has the correct number of petals, the correct location, and the tips of the petals are all in the right place. So that would be considered a winner as far as what we're doing here goes. Okay, so part B, let's have you graph r equals -5 times cosine of 3 theta. Again, a super good time to pause the video and see what you can do on your own. There's more than one way to do this problem. One way would be to set r equal to -5, and then the other way would be to set r equal to +5. Do not do both. You only want to set r equal to plus or minus your a value when you have an even number here, because you're looking for double the petals. So for this problem, it's really important that you either set r equal to +5 or you set r equal to -5. Now, if you set r equal to -5, which a lot of people kind of obediently do, then when you solve for your angle measures, you need to realize that those are the angle measures that give you an r value of -5. So you'd have to go away from them 5 units, not toward them, to get the tips of your petals. So for that reason, because I think it's simpler just to set r equal to +5. So if I set r equal to +5, I'll divide over the -5 over, like so. And then think about the unit circle. You're looking for when is cosine equal to -1. So you're looking for when your angle, which is called 3 theta, would be, who's that? That's pi. And then you'd have to add a full rotation of the unit circle or any multiple of that to get back. So divide both sides by 3, and then you'd have a nice little formula that would generate angles that give you r values of +5, because that's what I asked for. Okay, so now let's turn that into an actual graph. So if you let n equal 0, then you'd have pi over 3. So I'm going to go toward pi over 3, 5. Why toward it? Because I solved for this angle by setting r equal to positive 5. So pay attention to what you ask it for. So 1, 2, 3, 4, 5. Okay. And then I should add basically a third of the circle, or 2 pi over 3 to that. So 2 pi over 3 plus pi over 3 is pi. And then pi plus 2 pi over 3 would be 5 pi over 3. And then halfway in between, you know, you'd get kind of sucked into 0 essentially. So since there's only 3 petals here, you're going to end up with pretty wide petals. Goes through the pole, probably came down and got this guy. Okay, and I hope you know that, like, it doesn't really matter what order you draw the petals in, as long as they don't overlap and they all kind of start and stop at the pole, and then the tips are at the right locations, then you're good. So, all right, my friends. Hopefully at this point you feel fairly good about graphing rose curves, whether you have an odd number in there or an even number in there. And if things are not making sense, I hope that you will contact me and ask questions. All right, take care, everybody.